Now we are going to be looking at maximal intensity exercise with a short duration. These sports involve the athlete working at their maximum intensity, so using a large amount of ATP to generate a powerful force so they can perform maximally. Sports that are considered maximal are 100-metre sprints and mainly athletic events like shot put or long jump. This is because they involve the athlete to produce a large amount of force in a short period of time, so the muscles can work forcefully. These types of exercise use the ATP-PC system, as they are intermittent exercises. So, for example, in shot put, the athlete will throw once and then have a recovery break, then throw a further 2 times, so it is not continuous, and therefore the energy needs to be produced quickly and be accessible immediately from the muscles, which is where the phosphocreatine is stored in the muscles. These sports would be using their fast glycolytic fibres because the muscles would be required to generate large amounts of force in order to allow the body to produce the force. So the motor units are larger and there are more within the muscles, and they would be recruited in order to produce this force. However, the ATP-PC system only provides enough energy for the first 10 seconds of a sport. So for the 100-metre sprint, typically this is achieved in around 10 seconds or slightly over. So the athletes would be using the ATP-PC system as their dominant system. But in contrast to a 200-metre sprint, the athlete would be using their ATP-PC system in the first 10 seconds, but as the stores are depleted very quickly from the muscles, and the ADP needs to be resynthesized into ATP, the athlete then has to divert to their glycolysis system in order to prevent their rapid decline in power. So this means then they can continue the race, but now glycogen has become the energy source, which is broken down into glucose and pyruvate in order to provide the ATP. And this system provides a net gain of 2 ATP. So 4 ATP go into breaking down the components, and we gain 2 ATP from this. However, a limitation of this system is, as a result of this, it produces waste products such as lactic acid and hydrogen ions, which increase the acidity in the blood and decreases the pH. As a result, it then builds up in the muscles and prevents the athlete from sustaining their intensity, and therefore they are forced to slow down, or their throw is affected in how much power is generated, because the increased acidity means they have a lower resistance to fatigue. So the hydrogen ions in the muscles accumulate, and then therefore that causes the soreness and the muscle cramping, and the muscles become stiff, so the athlete can no longer perform at that intensity and they're forced to stop or slow down. So this is one of the main reasons why we fatigue, and as shown on the slide, the depletion of the ATP and PC stores and the energy stores, because our bodies are not able to replenish these at the demands required. So if we are not hydrolyzing the stores at the rate needed, we will not be able to generate enough ATP for exercise. So now we're going to move on and talk about the 100-metre sprint as an example. So because it's a maximal sprint, they'll be using the ATP-PC system where the phosphocreatine is stored immediately in the muscles, but it will only provide, as we said, with 10 seconds of energy. So then we are forced to use glycogen as the energy provider by the glycolysis system. And as we said, the lactic acid forces the performer not to work at their maximal intensity. So in order for the body to be able to function properly, the blood pH must remain above 6.4. If it drops below this, then it can greatly affect the functioning of the muscles, which, as we said, and the neuron transmission to these muscles and the motor units, which impacts the muscular contraction and therefore the amount of force that can be generated. Because this acidity has built up in the muscles, it affects the velocity and the force that they can generate. so they can't contract to the same density and force as they were before, and therefore they become less sufficient, and the performer, as we said, has to stop or perform at a lower intensity until the lactic accumulation can be broken down rather into glucose and used in the body to produce products of ATP, broken down into glucose and glycogen to be produced into ATP, or attempt to be removed. And obviously this takes time, and as we will look at in recovery, it's important to consider the recovery time needed to replenish these stores before taking part in exercise again. In sport, there are several reasons why athletes fatigue, and these factors must be accounted for and replaced during recovery, otherwise the body cannot continue working at the required intensity. This is why it is vital that the body returns to its pre-exercise state, so it can then replenish all the stores needed to participate again. So one of the causes of fatigue is the depletion of the energy stores, which we've said. And when the body stores of glycogen have been depleted, they can no longer perform at that intensity. We also need the energy to allow the myocardium to contract forcefully and force a greater straight volume of blood to the skeletal muscles. The energy we use in the body is supplied from the foods we eat. So, for example, carbohydrates that we gain from starchy foods are hydrolyzed into glucose, and that's then used to generate ATP. Similarly to fats into fatty acids and proteins into amino acids. So if the athlete doesn't have enough of these stores, then the energy stores will be depleted very quickly. And obviously carbohydrates produce the most energy for ATP, and which is what we want to have the most of our glycogen stores. However, if these deplete, then we are forced to use fatty acids or amino acids, which take longer and don't produce as much force, which is why they're mostly suited for the longer duration activities and the lower intensity, because they produce the energy over time. The phosphocreatine is synthesized in the liver and is used by the muscles where it is stored to be used during intense efforts in exercise. So linking back to the previous example of a 100-meter sprinter, while muscle and liver glycogen is different in where it's produced, there is an insufficient availability for oxygen and ATP. This in turn results in the reduced rate of ATP synthesis because the depletion of the glycogen and PC stores means that muscular contraction is difficult to contain. So the muscles cannot provide the force needed for this race, so the athlete will be forced to slow down before the line, which therefore may cause their position in the race to be, in the competition, to be sacrificed. Here we have a diagram to demonstrate the different stores in exercise and their volumes at pre and post exercise. And this is demonstrating the sources of energy and the metabolic responses by the body and how we are using the stores in order to produce the energy needed. So firstly, we have the ATP content, and in the slow oxidative and fast glycolytic fibres there is a volume of 24 millimoles in slow oxidative fibres and fast glycolytic fibres as well. But we can observe that at post-exercise, so during the recovery phase, that the slow oxidative fibres now have 20.6 millimoles and the fast glycolytic have 19 millimoles. So therefore, they have both lost ATP during exercise as it's been used, but the fast glycolytic fibres have lost more than the slow oxidative fibres. If we then compare this to the PC content, we can observe that the values drop from 79.3 to 5, and the glycogen content from 472 to 346 in the fast glycolytic fibres. So we see a much larger decrease than we do in the slow oxidative fibres, even though they've also lost the energy stores. It shows that the stores have been depleted because the fast glycolytic fibres use their stores very quickly, when they are working without oxygen, to a point where they cannot be replaced. And therefore, not being able to replace the stores, the athlete is forced to reduce their intensity or even stop. And this diagram is illustrating that having fuels available in the body is very important so we can reduce and prolong fatigue. So this then allows the athlete to continue in their sport without being forced to stop, because they're able to conserve these sources so they don't deplete as quickly as normally they would by long-term adaptations. Here we have a graph that is showing the depletion of the phosphocreatine stores in the maximal exercises from rest to during exercise and in the recovery phase. So Casey conducted a study into the phosphocreatine depletion, and he found that as a result of the maximal exercise, the PC stores nearly were fully depleted, and this is shown on the graph. We can see that at rest, the athlete's PC levels are around 3.2, and in the muscles, they therefore have enough energy to produce ATP, which then can initiate the muscular contraction. But as the athlete begins to endure the exercise, the levels of phosphocreatine start to deplete quite rapidly to around 0.7, where they are nearly depleted, and to a point where the athlete can no longer continue at that intensity because their stores are too low, and therefore ATP is not being resynthesized into ATP at the rate that the intensity is demanding. So if these stores become fully depleted, then the athlete will experience fatigue, and therefore their performance will be compromised due to this causing a decline in the power that they can produce. After post-exercise, during the recovery phase, we can observe that the levels of phosphocreatine start to increase quite quickly, up to around 2.7. They have not been fully replenished, which is important to note, but providing adequate recovery time will allow the levels to be fully replenished so the muscles can perform at their maximum again. As if the athlete is given sufficient recovery time. If they're not given sufficient recovery time, then the stores cannot fully recover, and then this then affects the muscles and the overall performance in further events or the remaining duration of the event. And Salin found that the decline in power is a result of the depleted PC stores, which we can observe from the graph. This links to the recovery ratio concept, in that the athlete should find a balance between their training and the recovery needed to allow the body to adapt. Because if the training is strenuous, it can often result in injury if not enough recovery time is allocated. It is important to reduce the risk of injury and to allow all the stores to be replenished so the performer has enough energy to perform well. The typical ratio, if we look at in a runner example, is 3:1, where the training block will consist of 3 hard weeks of training, followed by a recovery week. This then helps them to fully recover and prevent the risk of injury, and make sure their stores are fully replenished so they can repeat the training program again. So the recovery ratio is whether the recovery the athlete has is long enough to replenish the PC stores. So what athletes do to help improve their tolerance is they reduce the recovery time in order to replenish their stores, and this then helps them in their exercises and their sports to make sure they're replenishing all the stores properly and that they have enough time in order for their muscles to be fully replenished so that their performance doesn't deplete as the exercise goes on. Now we are going to be looking at the idea of creatine supplements, which are used as a strategy to combat fatigue. In sports that are intermittent and involve the athlete repeating the action, for example in shot put, some athletes choose to take creatine supplements to try to reduce the fatigue and therefore to stop the reduction in their power. So here we have a diagram that is showing a comparison between the athletes who took a creatine supplement, which are represented by the black bars, and those who didn't by the striped bars, the control group. This is Casey's study that to determine the effect on the two different athletes, whether they had